intervals of time. Examples of periodic motion are movement of hands of a clock, the pendulum in grandfather's clock, a rocking chair, heartbeat, the rotation of the blades of an electric fan, and the movement of Earth about its axis and about the Sun. A body undergoing periodic motion always has a stable equilibrium position. The equilibrium position, also known as a resting position, is the position assumed by the body when it is not vibrating. A restoring force is the force that tends to restore a body from its displacement to its equilibrium position. The amplitude, or A, of abbreviation is maximum displacement of a body from its equilibrium position. The period, or T, of a body in periodic motion is the time required to make a complete to and fro motion. One complete to and fro motion is called a cycle. Period is usually expressed in seconds. Frequency, or denoted by lowercase letter f, is the number of cycles per unit time. Its SI unit is Hertz, abbreviated as Hz. 1 Hertz is equal to 1 cycle per second. Frequency is the reciprocal of period. We have f is equal to 1 over t. Sometimes angular frequency, or omega, is used instead of frequency. Angular frequency is commonly expressed in radians per second. The relationship between angular frequency is given by omega is equal to 2 pi f, or omega is equal to 2 pi over t. Simple harmonic motion, or SHM, is a type of periodic motion where the restoring force is proportional to the displacement of the body from its equilibrium position. This restoring force acts in a direction opposite that of the displacement. In equation, we have F sub S is equal to negative kx, where F is the restoring force or spring force. X is the displacement from equilibrium position, and K is a proportionality constant. The negative sign simply means that the restoring force and the displacement are oppositely directed. Simple harmonic oscillators are the systems exhibiting simple harmonic motion. The simplest form of a simple harmonic oscillators is a body of mass n oscillating on one end of an elastic spring, also known as the mass spring system. An external force can cause objects like springs to stretch or compress by a certain displacement represented by x. This force is numerically equal to the restoring force but opposite in direction. Thus, F is equal to kx. The proportionality constant K is called the force constant of the spring. It is the force needed to produce a unit of elongation or compression of the spring and has the unit of N per meter. The force constant K is a measure of the stiffness of the spring. A small value of K indicates that the spring can be easily stretched or compressed. In other words, spring with lesser spring constants will have greater displacements than those with larger spring constants for the same amount of force applied.
For our first example, an oscillating body takes 0.8 seconds to complete 4 cycles. What is the period, frequency, angular frequency of the body? First, we are asked to determine the time taken to complete one cycle. We have t, which is equal to time over number of cycles, which is equal to 0.8 seconds over 4, which is equal to 0.2 seconds. Substituting the value of t in equation 8.1, we have F is equal to 1 over t is equal to 1 over 0.2 second, which is equal to 5 second to the negative 1, or 5 hertz. We have omega, which is equal to 2 pi f, which is equal to 2 pi times 5 hertz. Now omega is equal to 31 and 4200 rad per second. For our next example, a force of 3 Newton elongates a spring by 6 centimeters. What is the force constant of the spring? How much force is needed to elongate the spring by an additional 6 centimeters? To solve this, we use equation 8.4 and substitute the values. We have K is equal to F over X, which is equal to 3 Newton over 600 meter, which is equal to 50 Newton per meter. For second question, F is equal to Kx, which is equal to 50 Newton per meter times 1200 meter, which is equal to 6 Newton. Let us now proceed with energy, velocity, and acceleration of a simple harmonic oscillator. The total mechanical energy of a mass spring system is the sum of its potential and kinetic energies. In symbol, E sub m is equal to U plus K, which is equal to 1 half kx squared plus 1 half mv squared, where v is its velocity at a distance x from its equilibrium position. If there is no friction, the total mechanical energy of the system remains constant. When an object is at its maximum displacement and amplitude, its velocity and hence the kinetic energy is zero. In this case, displacement x is replacement by amplitude a. The total energy will then be E sub m is equal to 1 half Ka squared. Note that the total amount of mechanical energy is conserved. Thus, 1 half Ka squared is equal to 1 half Kx squared plus 1 half mv squared. Using equation 8.6, we can express speed as a function of position. V is equal to the square root of k over m times a squared minus x squared. Note that the speed is maximum when x is equal to 0 or at the equilibrium position. The acceleration of a simple harmonic oscillator as a function of position may be obtained using Newton's second law of motion. A is equal to F over m, which is equal to negative kx over m. Note that acceleration is maximum if the displacement x is maximum, which is equal to the amplitude. For our first example, a simple harmonic oscillator consisting of a 2.5 kilogram body is attached to a spring with force constant of 275 Newton per meter. Its maximum speed is 655,000 meters per second. Find its amplitude and maximum acceleration. To solve this problem, note that velocity of an oscillator will be maximum if x is equal to 0. Manipulating equation 8.7 to solve for a and substituting values, a is equal to v times the square root of m over k, which is equal to 6,500 meter per second times square root of 2.5 kilograms over 275 Newton per meter, and that yields to 62,000 meter. Note that acceleration is maximum if the displacement is maximum or equal to the amplitude. Using equation 8.8, a is equal to negative kx over m, which is equal to the absolute value of negative Ka over m, and that is equal to 275 Newton per meter times 62,000 meter over 2.5 kilogram, and that yields to 6,8200 meters per second squared. For our next example, a 6,500 kilogram body when attached to a spring of force constant 225 Newton per meter oscillates with an amplitude of 1500 meter. Find the velocity and acceleration of the mass when it passes its equilibrium position. First, to determine the velocity of 6,500 kilogram body when it passes its equilibrium position, we will use equation 8.7. V is equal to the square root of k over m times a squared minus x squared. Substituting, we have square root of 225 Newton per meter over 6,500 kilogram times 1500 squared minus 0 squared, and that yields to 2,7900 meters per second. When the mass attached to the spring passes its equilibrium position, x is equal to 0. We now have a is equal to negative kx over m, which is equal to 0 over 6,500 kilogram, which is equal to 0. Let us now have the period, frequency, and angular frequency of a simple harmonic oscillator. Let us consider an oscillating body as a revolving object that makes one complete revolution equal to one period t. The speed v of this body is the circumference of the circle divided by the time. The maximum speed is obtained when the radius of the circle is equal to the amplitude. Therefore, v sub max is equal to 2 pi a over t. Note that oscillating body is moving at its maximum speed when x is equal to 0. Therefore, from equation 8.7, v sub max is equal to a times the square root of k over m. We can solve for period by combining equations 8.9 and 8.10. We now have t is equal to 2 pi times the square root of m over k. Since frequency is the reciprocal of period, F is equal to 1 over 2 pi times the square root of k over m. From equations 8.2 and 8.12, the angular frequency can be expressed as omega is equal to the square root of k over m. For our first example, when a 2.5 kilogram object is suspended from a spring, the spring stretches by 500 meter. What is its force constant? If the suspended mass is set into vibrations, what will be its frequency? First, we manipulate equation 8.4 to solve for k and substitute the values. K is equal to F over x, which is equal to mass times the acceleration due to gravity over x, which is equal to 2.5 kilograms times 9.8 meters per second squared over 500 meter, which is equal to 490 Newton per meter. Using equation 8.12, frequency F is equal to 1 over 2 pi times the square root of k over m, which is equal to 1 over 2 pi times the square root of 490 Newton meter over 2.5 kilogram, which is equal to 2 and 2300 hertz. For our next example, in the laboratory, you attach a 300-gram object to a spring of negligible mass and start oscillating it. The elapsed time from when the object first moves through the equilibrium position to the second time it moves through that point is 2 seconds. Find the force constant of the spring. We have the mass of an object that is 300 grams and a period of oscillation that is 2 seconds. And to determine the force constant of the spring, we use equation 8.11. T is equal to 2 pi times square root of m over k. 3, 2, 1. By manipulating the formula, we obtain k is equal to 4 pi squared m over t squared. In substituting the given values, we have k is equal to 4 pi squared times 0.3 kilogram over 2 seconds squared, which is equal to 2 and 9600 Newton per meter.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!